Okay, so today we have Quentin Lamouret, who will tell us about classifying magnetic quivers with a isolated Coulomb branch singularity. Take it away.
So thank you. Hello, everyone. Thank you very much, Julius, for the invitation. So today I'm going to talk to you about these two papers that we wrote with Antoine, Sinan, and Marcus, all regulars of this Quiver Meeting. And so it's all about classifying magnetic quivers whose Coulomb branch has an isolated symplectic singularity. So first, I'll talk about generalities, about SCFTs, the link with symplectic singularities, why we care, what are magnetic quivers, and so on. Then I'll present the fission and decay algorithm, which was the main technical tool that we used in those two papers. And then the last two sections will be about the two articles. The first one deals with the case of theories where the gauge group is abelian. And then the last, with this technical step done, we'll be able to turn to the general classification. Also, if you have at any point questions and remarks, or I'm not being clear, feel free to interrupt. Okay, so probably a lot of this will be known to most people in the audience, but let's go through it quickly. So quantum field theories and super conformal field theories, when they have 8 supercharges, have typically a large moduli space of vacua, and the geometry of this moduli space is highly constrained by supersymmetry. So typically, there will be some branch of this moduli space which is hyperkähler, and this is the case for the Higgs branches in 3, 4, 5, 6 dimensions, who are parameterized by the vacuum expectation values of some scalar in hypermultiplets, as well as in 3 dimensions, the Coulomb branch, which is parameterized by the scalars in the vector multiplets. Relatedly, in 3 dimensions, there is this 3D mirror symmetry, which is a duality between different 3D n equal 4 superconformal field theories, which exchanges the Coulomb branch and Higgs branch. And this will play a role later. Now, those Coulomb and Higgs branches are hyperkähler manifold, as I said, but so they have a metric as well as 3 complex structure, which satisfy a bunch of conditions. But if we forget about the metric, single out one complex structure, and then combine the two other, they combine into a holomorphic symplectic form, and the spaces are known as have the structure of a symplectic singularity. So it's this slide. A symplectic singularity. Their coordinate rings, so the ring of holomorphic function of those spaces, are the chiral rings of the SCFTs. So, for example, for the Coulomb branch, they contain the monopole operators, the PPS monopole operators of the theory. This chiral ring is graded by the conformal dimension, so we can count operators with a fixed conformal dimension and take the generating function, which is called the Hilbert series. And this is important because it's a geometric invariant for the symplectic singularity, and it's almost characteristic, meaning that it's very rare for two symplectic singularities to have the same, two different singularities to have the same Hilbert series, if it ever happens. Okay, another geometric invariant is this Hasse diagram. So these symplectic singularities are singular spaces, meaning that they have a singular locus. And there is a theorem that says that this singular locus, as well as the transverse slice between so transverse to the singular locus in the whole space, are themselves symplectic singularities. And so we can iterate this and look at the singular locus of the singular locus and so on. And we get what's called a foliation, where each leaf and each transverse slice are themselves symplectic singularities. They form a partially ordered set, where we say that one is smaller than the other if it is included in the closure of the larger one. And for example, typically the smooth locus will be the largest leaf because it is dense, and so all the other are contained in it. This forms a finite partially ordered set, which we can represent as a Hasse diagram, and so I'm going to give examples later. And for Higgs and Coulomb branches, this diagram encodes the phase transitions that can occur in the theory.
So I have a question.
Yes.
There are many symplectic singularities which show up as moduli spaces of supersymmetric field theories which are not conformal. So in this case, you exclude those options?
So as far as I understand, if we want there, if we wanted, if we wanted to,
or maybe you want to change your notion and call it a supersymmetric field theory instead of conformal?
Maybe it is important that there is a singularity, but indeed conformality is not is not critical.
Okay.
Okay. So a first example, maybe you look on the left. This is a very schematic picture of what it can look like. So in blue we have the whole space. In red we have the singular locus, which is maybe the union of two lines. And then those lines are themselves singular at the origin, which is also their intersection. And so in that case, the Hasse diagram would look like this, with at the top the regular locus, at the bottom the origin, the two leaves in between. If we, on the right-hand side, on the left-hand side of the screen, we have at the bottom 3D n=4 Quiver gauge theory. And if we look at the Higgs branch of this, then we can find the Hasse diagram by Higgsing more and more, so giving vacuum expectation values to more and more operators. And because we want to do this while preserving supersymmetry, it's very constrained, and these are actually the only possibilities, and they form this partially ordered set. So now I talked about Hilbert series. So for the Coulomb the 3D Coulomb branches, the Hilbert series is given by this monopole formula, which is given by this. So if the gauge group is the product of one unitary group of the correct rank for each vertex, and we divide by this diagonal subgroup which acts trivially, then the Hilbert series is given by this formula, where so lambda here is the lattice, the co-character lattice of this group. So we get a copy of z to the n for each vertex, and we mod out by the diagonal z. W and Wm are the Weil group and stabilizer subgroup, but they will not play a major role in our story. And then 2 delta m is the conformal dimensions of the various monopole operators. And so for each vertex, for each edge between two gauge nodes, we get a sum like this, where we have the absolute value of the difference between the magnetic charge at one node and the magnetic charge at the other. And then we have also contribution for the adjoint representation on each vertex. Okay, so magnetic quivers, it is a slight generalization of the setup, where these are these little combinatorial objects, which look like they could be quivers for some 3D n=4 gauge theories, but have this non-simply less, can have these non-simply less edges. So they are not always, they don't always have this they don't always have this interpretation, but we can still define their Coulomb branch, and they're useful because these Coulomb branches can be identified with the Higgs branches of some theories in higher dimensions. So this one here is the affine-Dynkin diagram for G2, and I've written the adjacency matrix next to it. So because we have this triply less edge here, we put a 3 and a 1 in the adjacency matrix, which is no longer symmetric. This one here is a slightly more complicated example, which is perfectly fine. But just as in the case of just out of Deakin diagrams, there is a notion of length, meaning that when we have this non-simply less edge, we want to be able to say that one node is longer than the other by a factor of 3 in this case. So for this quiver, this makes perfect sense, but for this one it doesn't, because this node would have to be twice longer as this one, but also 3 times for the other direction. And so we will restrict ourselves to quivers which admit this kind of length function. So this one will be excluded. Okay, great. So now for magnetic quivers, as I said, we can define the Coulomb branch. In particular, we have a monopole formula, which is very similar to the one for quiver gauge theories. It's exactly the same, except that now lambda, again, the same is direct sum, but the z by which we divide can be a bit different. Typically, it will have entries which are proportional to the inverse length of the various nodes. And in the delta, we have here contributions. We have here factors of the entries of the edges symmetrics. So for example, when we have here a triply laced edge, we'll have a contribution where we have 3 times the magnetic charge of the U2 nodes minus the magnetic charge on the U1. And this defines Hilbert series and a Coulomb branch. Okay. So now, the fission and decay algorithm is a way to compute the Hasse diagram of a magnetic quiver. So the way it works, the idea is that we can find all the entries in the Hasse diagram by considering the quivers that we get from the original one with the same adjacency matrix, but by decreasing the weights. So 2 things is, one, we only keep the good quivers, and so in simple case it's only the balance conditions, but I'll come back to this later. And the other thing is that sometimes you have 2 good quivers such that the sum of their weights is smaller than the weight of the original quiver. In that case, we include a leaf, which is the product of the 2, and it could be more than 2. And this here is called the fission by analogy with nuclear physics. So here the partial, I haven't included the last leaf, for example. But let's look at a full example. If we look at the theory that we had earlier, that this is the diagram for the Higgs branch, and we can also compute its mirror by 3D mirror symmetry, and then apply the. So we can 2 things. We can apply the 3D mirror symmetry at each leaf, but we can also to consider only the one, remove the flavor nodes by adding one U1 like this, so that we get the kind of unframed quiver to which we can apply the decay and fission algorithm, and then just consider all the smaller set of weights that we can and order them by comparing the weights, and we get indeed the same diagram. So this is one simple case, but we can check it on many more examples, and it seems to work quite consistently.
Question?
Yes.
The algorithm works only in cases where a mirror exists?
No. It works also in non-simply less cases for which there is no 3D theory.
So this is only a test.
Yeah, this is only a test.
Okay, thank you.
And but it's the kind of test that will be relevant to mine. I could have given many more examples related to 5D brainwaves, to a bunch of 4D n=2 constructions, and it seems to work. Yeah, it works consistently.
Okay.
This is indeed a very simple example. So which quiver do we need to take? So we need to keep only the good quivers, so the one which corresponds to indeed a CFT or a field theory where nothing decoupled in the infrared. So in particular, they need to satisfy the balance condition. So the first one would be excluded because of this, because the node in the middle is not balanced. Twice the weight of the node is 4, which is smaller than some of the weight of the neighbors. We also exclude the quivers whose Coulomb branch is the non-instanton moduli space. So typically these are affine Dynkin diagram times n, so all the weights multiplied by n with some added un. In this case, we have to remove them, but we would keep like another leaf would be the same quiver without the u1. And in the abelian case, the situation is a bit more complicated because some theory can be free. Indeed, we'll see later that this quiver, even though it's balanced and is not really an instanton moduli space, corresponds to a free theory, and so it will not, it will be excluded and will not correspond to a symplectic leaf. But we'll go. Okay. Yeah. So now we can turn to the abelian case. Okay. So abelian magnetic quivers, so the one where all the nodes have weight 1, they all correspond to quiver gauge theories, and in that case, the non-simply laced edges just mean that the corresponding hypermultiplets will have charge 1 for one U1, and then L if the edge is L laced. And so in particular, we can study the mirror theory and its Higgs branch, and we have control over everything. So to construct the mirror theory, in that case, in this situation, what works well is this co-kernel method, where basically, so we take a theory, where the gauge group is this U1 to the R. There are maybe n hypermultiplets, and the representation theoretic data is given by this charge matrix, where which gives the charges of the various hypermultiplets under the various factors of the gauge group. And then the claim is that the group of charges of the mirror theory is the quotient of z to the n by the image of this matrix, and the charges of the hypermultiplets, there will be n hypermultiplets in the mirror, and the charges of them are the images of the canonical basis elements in this quotient. So concretely, what does that look like? So if we take this quiver gauge theory, the charge matrix is given by this matrix. So here, each line corresponds to a hypermultiplet, each column to a gauge group. And so, for example, this link could be this first line, which has charge 2 under this node and charge -1 under this one, and so on. And so what the claim is that the group of charges of the mirror is z to the 5 generated by the x1 to x5, quotiented by this matrix, the image of this matrix. So each column will give a relation between the charges. So for example, the first column gives 2x1 minus x3 equals 0, which is this first equation. And the other columns will give other equations, and you get this system. So basically, this is a presentation by generator's manipulation of the group of charges of the mirror. So to solve this and figure out what groups this generates, we can do it by hand. We define y1 and y2 as follows. And then we can use these equations to express the x in terms of the y's, and the remaining equations give conditions on the y's. In that case, we get only one relation, which is that 2y2 is 0. So we see that y1 generates a factor of z, y2 generates a factor of z over 2z. And so we see that this is the charge group, and correspondingly, the gauge group is u1 cross z over 2z.
How do you choose the sign?
So the idea is that so if we could choose an orientation of the quiver, and then we have a positive charge at one end, a positive charge at the other. It doesn't, yeah. So it's just that we can, if we change the orientation, it corresponds to multiplying the line by -1, which will not change the equation and the quotient, and corresponds to exchanging q and q tilde in the hypermultiplets. And we can also, yeah.
It's changing sign for a whole column?
A whole column or a whole line.
I see.
Either is perfectly, it doesn't change the construction.
I see. So you could, and that would affect also the diagonal, right? The diagonal could have all positive.
Yeah. Because
there is some freedom in choice of sign.
Yeah, the choice of sign is arbitrary. I mean, not all the signs are independent, but there is a lot of freedom to choose the signs correctly. And the diagonal itself doesn't have a lot of meaning because the lines are hypers and the columns are vector multiplets. So the diagonal is not special.
Okay.
And so, okay, so here we get u1 and 0 to z, and then from from this set of equations, we can read the charges of the various hypermultiplets. So for example, x1 has charge 1 under the u1 factor and charge 1 under the z2. So it's the hypermultiplet in the middle here. x2 will have charge 1 under the u1 and no charge under the z2. So it's this guy. x3 has charge 2. So it's this guy. And then x4 and x5 are not charged under u1, but are charged under y2. So there are the two hypermultiplets here. So now we can do two things. We can figure out how what the pattern of Higgsing of this theory is, and we can apply the Decay and Fission algorithm to this guy over there. If we do this, we get this, and we see that indeed first the diagram match, and on each leaf we can match the quiver on the magnetic quiver on the left to its mirror on the right. So everything is consistent, everything works well. Okay, so next condition, a case where it's a bit more complicated, and we start to see the technicalities proper to the particular to the abelian case. If you consider this quiver with a p-aced edge on the left and a q-less edge on the right, The charge matrix is this thing. So yeah, with one hyper of charge p n minus 1 and the other one n minus q. If we do again this whole co-kernel thing, we have two hypers in the mirror with charge x1, x2. They satisfy px1 equals 0, x1 equals x2, and qx2 equals 0. And so this is solved by this here. Basically, the gauge group will be z over delta z, where delta is the GCD of p and q. And the two hypers will have charge 1 under this group. In particular, we see that if delta equals 1, then this is a trivial group, and we have just a free theory of two hypermultiplets. And by 3 mirror symmetry, the thing we started with will also be free. And so in particular, this thing, when p and q are co-prime, should not appear in any Hassett diagram that we draw from the fission and decay algorithm. However, if p and q are not co-prime, then this is a good quiver, and we keep it. Okay, so now we add one more layer. We look at the one at the bottom here with k, p, and q. Now, here we can again do, so I'm not showing it, but we can again do the same co-kernel construction. And what we figure out is that if k and q are co-prime, then there is one of the hypers in the mirror which is decoupled. It's free, and so this will in that case is not a good quiver. However, if k and q are not co-prime, then there is a discrete gauge group in the mirror, and the theory is good, and we keep it. However, and likewise, the one in the middle will appear if k and p are not co-prime and will not be there. So what we see is that this one, if we want this one to be a good quiver and have a symplectic singularity and then its Coulomb branch, we need k and q to not be co-prime. And if we want this quiver to have an isolated singularity, so we want no leaf in the middle, then we want k and p to be co-prime. And yeah, okay. One other thing I want to show in this slide, in this example, is that each time the magnetic quiver has a cycle, then there is a U1 in the mirror. And this is again a general fact that's not too hard to check from the co-kernel, because basically when we have a cycle, we'll have condition relating the various the charges of the various hypermultiplets, and they will cancel to give one of the generators which with no relations, giving the U1. Okay, and now with those two observations, it's not too hard to see that the only abelian quivers whose Coulomb branch is isolated can have this form. So here we have a non-simply laced edge with some multiplicity. So the entries in the adjacency matrix will be Ln and n. And the corresponding Coulomb branch is this Kleinian singularity C2 mod Zn. Then we have this linear quiver. Here we need to impose a bunch of these GCD conditions, so a bunch of conditions on the GCDs of the various L's and K's. So here we wrote Lk with those two arrows to say that most of these arrows can be laced in either direction. So we put L1 for the condition, the lacedness in one direction, K1 for the lacedness in the other, and we always assume, I mean, it's simpler if we assume that L or K is 1, so that we actually get a symmetrizable quiver and a well-defined length. So here, what do we need for GCD conditions? We need the first L to be not co-prime to the last K. And we need all the other pairs of L's and K's that face each other to be co-prime. Yeah. So maybe I can show it here. We have the last the L1 and Kn need to be not co-prime, and to all the others that face each other, so L2 and Kn minus 1, for example, all of them need to be co-prime, so that there is no shorter quiver that is good and that would appear in the Decay and Fission algorithm. And the other one, the other case that we can have is a cycle. Then the mirror theory will have a U1, and here again, we have to impose GCD conditions to ensure that no shorted chain can appear in the decay and fission process. Yeah. So maybe I show them. The GCD conditions are no, here. So we need a condition between the L and the K's so that there is a well-defined length. And we need the pairs of edges that face each other to have this co-prime condition. Okay, so very good. So now with this classification of abelian ICSS, okay, yeah, maybe I comment on I finish commenting on the Coulomb branches. This is a Kleinian singularity C2 over Zn. This is maybe a higher dimensional generalization of this. This will be a quotient of C to the 2 to some power, so some even power, quotiented by some finite abelian group. We can figure out the abelian group, or some cyclic group even, from the GCDs of L1 and Kn. And this one will be a hyperkähler quotient of C to the 2n by U1 with some representation, some charges for the various C2 copies of C2. Okay, and now with this done, we can turn to the general case. So maybe I wanted to show an idea of how the proof in the general case work, but I'm going to restrict to the simply laced case. But the general case is the same. So the idea is that okay, if we look all the way here, yeah, maybe some remark I should have said. When we do the Higgsing or the decay and fission algorithm, the full quiver theory lives at the bottom of the diagram, and as we Higgs or move on the decay and fission, all those quivers, their Higgs or Coulomb branch gives the geometry of the transverse slice. So basically, the Hasse diagram that lives above of it, and in particular, on this side, all the leaves that go just after the last one, those are magnetic quivers whose Coulomb branch is an isolated singularity because they just in it. The Hasse diagram of this will just be this part, which is as simple as it can get. And
you
so
could also say that these are the effective theories that live on the leaf.
Yes, indeed.
Like you're really selling what remains on that leaf. So it's a very useful representation to do it this way.
Indeed. Okay, and so the idea of the proof here is that if we have the full list of magnetic quivers with an isolated singularity, then we know from the consideration that we just had that any magnetic quiver will at some point decay to one of the quivers in the list just before reaching the top leaf. And so to show that the list that we have is the full list of magnetic quivers with an isolated singularity, we just have to show that any magnetic quiver, will decay to one of the quivers in our list. So in the simply laced case, the list is quite simple. It's just the ADE classification, like the affine ADE Dickin diagrams, affine simply laced, yeah. And so we just have to show that any simply laced magnetic quiver will decay to a simply laced Dickin diagram, affine Dickin diagram. And so to do this, we start with this consideration. If our starting quiver has an edge with a multiplicity n, then we know that it decays to, oh yeah, I wrote A1. Actually, I should have written AN anyway. So it decays to the abelian quiver with two nodes and an edge of multiplicity n, which is in our list. So we can assume that this is not the case and restrict to the case where all the edges are simple, have multiplicity 1. Then if the quiver has a cycle, then we know that it decays to the corresponding AN Dickin diagram, which is in our list. So we can assume that the quiver we're considering has no cycle. So it's a kind of tree. Then if, so this, from this point on, there are some technical difficulties because so those two quivers here, the first two ones, were were abelian, all the weights were 1, and so we just had to find the shape in the graph. Now the D and E quivers have some weights that are greater than 1, and so to show that there is a decay, we actually have to show that the weight, we can assume the weight in the starting quiver to be greater than to be high enough so that this is actually a decay. I'm not gonna get into all those details, but it can be done. And the basic idea is then to show that if there is one node with 4 neighbors, then we can decay to this D4 decay diagram. If there are 2 nodes, so we can assume that there isn't. If there are 2 nodes with 3 neighbors, then we can use them to decay to this DN decay diagram. And so we are left with a situation where we have this star-shaped quiver with 1 node from which 3 branches grow. And we have to show that in this case, this will always decay, if it's good, to E6, E7, or E8. Yeah, and that's the main, yeah, that's a bit technical at the end, but it can be done. Okay, so now if we turn to the general case, there is one more subtlety, is that we can, when we have, yeah, let's do it in that way. If we have this, so this is E6, and we have these edges between one extremal, one U1 node at the end, and a node with weight more than 2 or more, let's say. And in that case, it turned out that we can turn this into a simply laced edge in this direction, as long as we don't create 2 edges that face each other and have non-co-prime lacedness. So in this case, we can put non-simply laced edges at every extremity, as long as all the GCDs are 1. And this will not change the Coulomb branch. And basically, this is because when we do this in the monopole formula, we change for the few edges that we change, we'll change the coefficients of the adjacency matrix here, but we'll also change the lattice by which we quotient. And it turned out that in this situation, both of the effects exactly cancel, and it doesn't change the monopole formula, and it doesn't change the Coulomb branch. Yeah. So yeah, then in the next few slides, there will be a bunch of those gray non-simply laced edges, but they don't really play a role. They're just this is a quiver, and if you want to classify all quiver, then they will be present. And so now we redo the same kind of game that we did in the simply laced case, but in full generality, and we get this list. It's on two slides. So this is the first. We get all the three slides. There are the abelian one that I showed earlier. Then there are all of these quivers which are affine Dynkin diagram, twisted and untwisted. So we get we get all of these. All of these were already known. The geometries are known. They are the minimal nilpotent orbits of the proper group. Wait, okay. Yeah, okay. And then this is the second slide. So this one is already known. It corresponds to Kleinian singularities, C2 mod some discrete subgroup of SU2. Then those 3 are relatively recent discoveries, both in physics and mathematics, but by now they are reasonably studied. And the 3 on the right-hand side were new, and yeah, they didn't, as far as we know, didn't appear before. And so we then turn to, okay. Before we go to study in a bit more detail those 3 quivers, a few comments on this full classification. So not all symplectic singularities are present. Not all known symplectic singularities are present, but all the ones that are not quotient singularities appear. Of course, you can, if you have a complex symplectic vector space with a finite group acting on it, you can hook up a bunch more symplectic singularities which are not here. But if we restrict to the ones that have trivial local fundamental group that are not those quotient singularities, then everything is there. everything known in there, and so presumably those three things here could be novel symplectic singularities. And so yes,
the singularity of Berry is going to show up here.
no, indeed, probably not.
And the reason is because
what is the singularity? I didn't hear. Maybe what is the singularity?
It's a very recent one that was found by Coulomb, who's a mathematician.
Oh, I see. Okay.
An article constructing a new singularity, which indeed is conjectured to not be a 3 Coulomb branch.
Mm-hmm.
So you're saying it's not going to be a Coulomb branch of some quiver?
Of some unitary, yeah, indeed.
It cannot be, right? Because he computed the Hilbert series, and because it's not a Hilbert series of one of those in the list, and this list is complete, so we know that it cannot be the Coulomb branch of a unitary quiver.
I see.
It could be of an orthosymplectic quiver or something else, but not of a unitary quiver.
I see. Okay.
Okay. And so then, yeah, you try to identify the three singularities on the right. To do that, we computed the highest weight generating function. So basically, it's like a fancier kind of Hilbert series, where instead of just counting the number of operators with a fixed conformal dimension, we also track the representation in which they transform under the group of isometries of the Coulomb branch in our case. And so more concretely, is this formula where the coefficients an and 1 up to nr is the number of operators with a conformal dimension n, which transform in the representation whose Dynkin label is n1 to nr under this Lie algebra that we have to find. And so what we found was that so it's this table. The three families have a quite large group of isometries and reasonably simple highest weight generating functions. So in particular, we find that some funny properties of this is that for the GBN and GDN, the highest weight generating function is independent of n. It's also the same for the two series. And so the only dependence in n is hidden in the choice of the Lie algebra, which is SO2n or SO2n plus 1, depending on for the corresponding two series. And then for GCN, the symmetry group is U to the 2n plus 1. And this is the highest weight generating function.
How is the choice of the name done?
The choice of the yeah. It's because this end of the quiver looks like a G2 quiver, like with a triple S ledge, and the other one looks like C, P, or D, respectively.
I see. And so the symmetries not always coincide with the.
No, no, it doesn't.
Okay.
So maybe the choice is.
Well, it's a choice.
It's a choice, yeah. For now, no better. We didn't have any better, I would say. Okay, and so from this highest weight generating function and discussing with thanks to the discussion with Paul Levy, we're able to identify the fact that the geometry of the GCN Coulomb branch is the same as the one of this one of the abelian ones that we had earlier, so concretely this one. And so this equality looks like some kind of folding operation, although the details of how this happens are not exactly clear. And yeah, as far as we know, the GB and GDN are genuinely new symplectic singularities that that don't appear elsewhere. Yeah, so to sum up, so we can use the Decay and Fission algorithm to compute the Hasse diagram of magnetic quivers with unitary gauge group. Okay, so one other thing that I didn't mention because I didn't need it is that we can also refine it to compute the geometry of the elementary slices. This allows us to classify the various Coulomb branches, the various magnetic quivers whose Coulomb branch has an isolated singularity, and it gives, in that way, a partial classification of isolated symplectic singularities. And in the abelian case, we had to use 3 mirror symmetry to deal with the various technicalities that arose in this case. And then perspectives would be to do this again, but with orthosymplectic magnetic quivers. So we'd have to do the Decay and Fission algorithm, figure out how it works exactly, and then redo the work for the classification. And then then this kind of idea could also be used to study how two successive slices can appear in a given Hasse diagram. So maybe a first step would be finding the quivers whose Hasse diagram has height 2. And the idea would be figure out in the Hasse diagram of the general symplectic singularity, which how can the elementary symplectic singularity be arranged. And because we have those new symplectic singularities, it would be interesting to find realizations of them as moduli spaces of some physical theories. So maybe with using brains, either as the full as the moduli space of some physical theory, or some elementary transition in the moduli space of one. And yeah, that's about it. Thank you for your attention.
All right, let us thank Quentin. Do we have questions?
Quentin, may I ask one question on those non-abelian quivers?
Sure.
Yeah, so for those quivers, you don't allow like the double list edges, right? The reason to satisfy the Lance formula?
So you mean several edges on the same node?
Yeah, and I mean like a double list edge. So here is just a single list edge.
Okay.
Okay, so
I mean like a PQ
yeah.
edge. Yeah, like a KL edge in your abelian case.
Okay, so indeed the condition that we impose is that the two of the diagonal coefficients in the adjacency matrix, one divides the other. So you can have multiple laced edge, like multiple edges, but they have to be all the same lacedness.
So a bit confused. Like if I choose a coprime PQ, then what's wrong with it?
Okay, no, actually, so in the abelian case, it doesn't change anything, and we can allow it. In the non-abelian case, it's a bit less clear the meaning of these PQ edges, but indeed, we expect that they don't. We expect that if we include them, the classification will not change much, except maybe basically having one GC with just 2 nodes and a 2-3 edge.
I see. And also I have a question on this Lance formula.
Just for this point here, what Quentin said, we in our paper we added at the end this thing, and I don't know if you have it there on the slides, but that's what he said, right? It just adds one quiver, so there is just one non-abelian one, which is this GC one. So you can take any one in the GC family.
Actually, I can draw it like this. So it would be something like 2, 3 with weights 2.
Yes. 2, 3, 2, 2.
Yeah, like that.
So it's a Coulomb branch.
Arguably, it should be where is it? How do I go back? There. Should be the Coulomb branch of this thing with
yes.
With the two 3 edges. No, with 2 3 edges, just a square would be my guess. We'd have to check.
We have computed the Hilbert series, and it doesn't match anything that we knew, but maybe you can recognize something else.
I see.
It should be that.
I see. Yeah. And also I want to ask the reason that you assume like this Lance formula. So what's the reason? Like, so you say if it's not satisfied, it cannot be like the Higgs branch of some higher dimensional series.
Which formula?
Like in the very beginning, you have this Lance formula, right?
The length function.
Length,
okay. The length function.
Yes. Indeed, as far as I know, every time you find a magnetic quiver from a higher dimensional theory, it has a length function.
Yeah, from Grunwald, it's I guess it's true.
Yeah.
But I don't know if like for more general.
I don't, okay,
so-
honestly, I don't know exactly to what generality it ends.
What did you
Another
say?
remark
Just
is
the
that
what?
whether the length, like, can there be magnetic quivers without well-defined length function from higher dimensional theories?
I mean, if the, like, a priori, if we don't talk high dimensional, then obviously there can, right? Like,
well, I mean,
especially in the abelian examples, it's
yeah,
like
in
not
the
a
abelian
problem
example,
at all to
it's
put
clear.
this. So
Indeed.
why not for other stuff? Like, you can still compute, or do you find some Hilbert series that don't make sense? I think it's purely if you want to do things with a closer brain system system, you put this notion.
I think the
Or if
question
you
was
want something
about brain
unframed.
system. Like,
Yeah,
can you
yeah,
find
yeah,
a
yeah.
brain
The brain
system which
system
gives a
is
quiver
clear.
which has no length function? That's the question, and we assume that no such thing is known.
Yeah.
They sure has suspicion that there is.
Well,
No,
I'm
I'm not saying. I'm just asking the reason why. Like from the
And-
burn construction, maybe this is something correct. But if we like, I'm seeing like maybe we can relax the condition. Like so we don't assume there is a burn construction, or we don't even need to like assume there is a higher dimensional theory correspondence.
Yeah.
Yeah,
Another
I mean,
reason why we
in 3D you could just have some, Coulomb quiver.
Yes,
And compute its Coulomb
magnetic
branch.
Coulomb quiver.
another reason why we impose this condition is that the like the second paper especially we wrote also for mathematicians, and the paper by Nakajima and Weeks, in which they construct the Coulomb branch of these magnetic unitary quivers, they
Yes.
impose the condition that there are no PQ edges and there is a well-defined length function.
But,
So we stated
mathematicians are, they
sure.
they're very, very close-minded. We are not shackled by any of this.
So could this be generalized?
Right?
Maybe.
Like,
Yeah,
who cares?
no, of course.
I mean, you can just totally go for it. And if you have an unframed unitary quiver where there is no notion of length, you don't even need to ungauge. So you can just go ahead and compute stuff like. So actually, this could really lead to some new things. I don't know, like possibly, yeah.
Yeah, so that's a limitation.
There's always a
that
question of.
We just decided to use this. The reason was physical, but then of course the whole other thing is open. So, and the show showed us actually some very nice example of such a quiver, which then is not in our list.
Yeah.
And of course, there's always a question. These non-simple-laced quivers, if they're abelian, they make complete sense. But if they're non-abelian, then we don't really know what to do with it. But they seem to make sense, but maybe not anything you cook up has to make sense. So it's a bit of, but one can just go ahead and try stuff, right? Move fast, break things.
Yeah, of course.
Cool. Craig, you have your hand up for 10 minutes.
Yes.
Oh, wow.
Yes. But I was enjoying hearing about the software development approach to physics. So I wanted to ask actually a very basic question. So you said that you want to keep only quivers that are good when you do this decay and fission. But of course, we know plenty of examples where I start from a quantum field theory and I Higgs it and I get another quantum field theory plus a free sector. So is the statement that those ugly quivers are not part of the symplectic singularity, or is the statement that you're sort of throwing them away because you're not interested in them?
Well, the idea is like when you Higgs and you move away from the singular points, the things that are massive decouple, like are integrated out in the infrared, but the things that basically the hypermultiplets that become free are the ones that parameterize the direction along the along the slice that is below you, and the quiver that we keep is the one that parameterizes.
Sorry. There are two sources of hypermultiplets, and you're talking about the opposite one I am. There are the hypermultiplets corresponding to sort of the thing you give a VEV to, which becomes massive and decouples along the flow.
Indeed.
But you can also have something which Higgsies to a quantum field theory plus sort of free massless hypermultiplet, so like a flat direction.
But a free massless hypermultiplet you can give a VEV to.
Sure.
So
But
it will also parameterize something in the slice.
Right,
so
it's
you
something
would-
like a transfer
in the
space, right? It's something
Yeah,
like a tangent space. It's not really giving left to these things doesn't really matter, right? The free hypers are just free hypers. They decouple.
Right.
In particular, they're not in the transverse slice that is represented by the
right.
So I think you can think of them as the really the tangent space to the leaf in the geometry.
Actually,
there's the transverse slice and then there's the tangent space. And locally, like in this construction of Kaleden, for example, like the free hypers are somewhat there. Like if you have a local patch of your leaf, then these are the free hypers. At least this is how I thought this works. Maybe it's not quite correct.
This sort of makes sense because you could imagine cooking up sort of some kind of symplectic singularity corresponding to Higgsing in one case of theory A to B, in another case of theory A to B plus free hyper, and you would expect these to be different symplectic singularities. And this seems to be, the decay and fission would seem to tell you these are the same guy.
Yeah.
So
yeah, because combinatorically, basically, like both for quiver subtraction and the decay and fission. So if you just keep applying the algorithm, so at the end you're gonna have something like which is intrinsically bad, which you cannot subtract anything, and then we can see like this is the smooth part, this is a free part, and so obviously, yeah, we can always apply those tricks no matter, because we only care about the singular part of the theory.
Okay. Maybe it didn't quite.
Just another way of answering this maybe is that it's not that we don't want the ugly ones. It's just that if we want there to be a one-to-one map between symplectic leaves and a set of combinatorial things, we just found that if you keep only the non-ugly ones, then it's fine. And the reason, of course, that the other ones are very nice, but they don't. If you keep them, then there is not a one-to-one map because the transition is non-singular. So you can keep them, then you decouple the free thing, but then they will correspond to the same leaf. So that's why if you want to count everything once, we decided to always remove them. We could have decided, oh, we always keep the ugly ones, but then we have to remember when we then remove the free thing, we should not count that thing that we arrive at. So it would lead to some more complicated things. So it's not really a physical reason. It's more to have a well-defined one-to-one map between leaves and quivers.
But I think it is making it a bit more complicated. If you have a singularity of codimension higher than 1, if you walk away from the singularity, you pick some direction to walk in. You could pick some coordinate system, so some field redefinition, that this is giving that to like one specific field. And now the other things, you can also, the other directions you can walk into for free without further desingularizing. So like think of a sheet of paper, a point, now walk to the left, now you can walk up and down. You could have also walked up, but the codimension of the singularity remains unchanged by this. So the stratification into the symplectic leaves is exactly what they provide with fission and decay. And these free hypers, that's why I mentioned the tangent space, it's just there. Now go ahead and move around in some other direction, that's completely fine. There's a codimension, and that's the key thing. It's codimension, and that's captured here. So you can take some quiver, unitary quiver, like change one of the UN nodes to UN -1. Now you have something with a bunch of pre-twisted hypers you can decouple in, like the normal case. Now you decouple all of them, and now you have the transfer slice. And all of these things you decouple are just extra directions that you can walk in, which are part of your codimension. So it's not there's no new information here that you can gather by keeping all these quivers. It's really just the notion of codimension, because the singularity has a codimension.
Yes. Okay, I see. Yeah. Okay, this makes sense. I see. I was worried we were being too cautious in sort of ignoring this ugly stuff, but okay, very nice.
Good example is the moduli. Sorry.
No,
moduli space of instanton is a good example. Quentin, you showed at some point there was a slide with this one, and if you keep it, I don't know where it was, but if you keep it, you would count this thing twice because there is one with the U1 added, and then with this one here. If you keep that quiver, which is perfectly fine, and then there is also the one without the U1, and then you would count 2, but you have to count only 1.
Okay, that's nice. Actually, we had similar issues in the orthosymplectic proposal where there were things that would appear twice, and we had to try and quotient by that.
It's exactly the same. So yeah, it's what Julius says geometrically, and that's combinatorially the simplest thing to do.
Okay, cool. Nice. Thanks. I had one more question if we still have a little bit of time.
Yeah.
Definitely.
Wait, which cases did you have issues in the auto-symplectic?
So there were cases where we had product theories which appeared twice. They appeared, for example, once as a product of two quivers, so you saw some fission process, but there were other quivers which were connected. So a single quiver whose branch was a product theory. This was the kind of examples.
Okay.
Yeah, so is there a clear obstruction to realizing these new slices, the GB and the GD, from a Higgs branch of something higher dimensional? I didn't get enough of a look at them to.
Yeah, that should be here.
Yes.
So we looked a little bit. The main technical issue is to realize these three triply laced edges, but I don't think there is an a priori reason that this cannot be.
Okay.
So, yeah, actually, there are two distinct questions, right? Is there a brane realization or whatever string theory? That's question one, and yeah, we tried a bit, and at the moment we don't have an answer. Then there is the Higgs branch question. Can you find a quiver whose Higgs branch would be the same as the Coulomb branch of that? And to that, actually, so unfortunately he's not here, and I don't want to spoil the thing, but Guhesh has a proposal, and I just wrote to him actually to ask him where it is, and so I don't know how certain he is, and I don't know if he wants to put it in a paper or something, but you can ask him. So there is presumably there is one. It reproduces the HWG. And then Guhesh, and maybe he's working with some other people in the audience who know. So I don't know. But
okay, I will wait for that instead of trying to come up with examples. Yes. Okay,
since this is recorded and so on, I don't want to spoil his thing. So let me not say what it is.
All right. I forgot we're still in the recording stage. Yeah, so thank you. I will let someone else ask questions.
Do we have more questions?
Maybe one more comments. Yes. So if you go to the conclusion part, like about this head to Hudson diagram. So here, then if you really want to do this, you have to also to consider all the non-normal varieties, right?
Indeed, yeah. And yeah, that's for sure. Which cannot be Coulomb branches of anything. So indeed, that's true.
Do you have any idea like how to classify the non-normal stuff?
I don't think anyone has, but I don't.
Okay. When we are off the recording, we can say a very wild conjecture.
Sure.
Oh wow.
Whoa.
All right. So any more questions before we can move off the record? Okay, so then let's thank Quentin again. And let's hear Antoine.